stars, and then I ended it with star type based on population. So if you have missed my lecture, I would advise you to reach to me or reach to Danny to get a link, a YouTube link for it. So because what I'm about to teach here is going to build upon what I've explained last. So in today's lecture, I'm going to be having some revision on star formation and evolution because some of them we apply in what I'm about to lecture today. Then I will talk about star type based on spectra and also star type based on mass. So last time I said that shock wave are agent that triggers star formation according to the simulation on your screen. So stars are formed from giant molecular cloud, okay? So when there is a supernova explosion, okay, the shock wave from the star, moves and, slams on this giant molecular cloud, and it creates what we call density differential, okay? So there are some regions that will have more mass, okay? Those regions will begin to attract other gas and dust to become bigger, and that is what we call the collapse of the giant molecular cloud. So a star begins from the proto star, okay? It begins to accumulate these gas and dust under gravity, okay? As it is growing, the gravity increases, okay? So, and as this matter are falling into the center of gravity of the star, okay, they generate heat because they slam onto themselves, so they generate heat, and that heat is trapped in these dust and this gas and dust, and the heat increases until 10 million Kelvin, okay? It increases up to 10 million Kelvin, and then um, proton to proton nuclear fusion is initiated, okay? There are other complicated things going on, okay? I won't talk about them, but this is just the basics. I mean, those things like quantum tunneling, it happens here, but for the simple case, this is just how a star begins to fuse hydrogen into helium. So from that stage, when the star starts fusing these hydrogen to helium, we say that the star has moved, or the main sequence star of the star have started. And that is where the star spends 90% of its life, okay? So here's a diagram describing the whole process. So two protons combine to form deuterium. Deuterium is an isotope of hydrogen, it's a heavier hydrogen. So releasing positron and a neutrino in the process. The deuterium then fuses with another proton to form helium-3, another isotope of helium, okay? And two helium nuclei collide to form helium-4, which is the one we know. So releasing protons. But these whole fusion processes generate heat, and that heat is used to support the star. Okay, the heat produces what we call radiation pressure. Okay, so the radiation pressure is going to be pushing outward while the matter that is falling inward, we call it weight, or we can call it gravity. Okay, so within the stage of a star, it is going to strike a balance. So that balance is called the hydrostatic equilibrium, and I have explained this last time in my last lecture. So if you don't have it, you better watch the video. But another important thing that I made mention is about this. I said, I showed this slide, I said, the more massive a star is, if you have two stars, one is very massive, one is less massive, okay? If you have a star that is massive, it is going to have more weight with respect to the core, okay? Not at the surface, with respect to the core, okay? That weight is going to generate pressure. You understand? Now, the pressure is what generates heat, okay? And then the heat is the fusion itself. You understand? So for a very massive star to be able to sustain the weight of that massive star, it has to be fusing a lot of hydrogen fuel to generate enough heat to sustain the mass. So let me just use this little scenario to make it, very simple and very understandable to you. So imagine a low-income US citizen. Okay, a low-income US citizen could spend, say, 25,000 US dollars in a whole year. Okay, so that low-income US citizen can be likened to a low mass star. And then you have a high-income earning US citizen, okay, who may be spending maybe 150 $150,000 in a year. Okay, but this high earning income person, has a lot of properties to maintain, maybe have a house, have a car, have a lot of properties to maintain. So those are the expenses. By the time you add up all the expenses, it becomes 150. But for the low income person, there's nothing much to spend. Now imagine a scenario where there is economic turmoil, okay, maybe inflation, okay. Now it will affect the high income earner more than the low income earner, because the income, the money that is flowing in from the business, it's not enough to sustain the lifestyle. So that is exactly what is happening for stars. For a massive star, it requires a lot of hydrogen to be able to generate enough heat to sustain its mass, its lifestyle. Okay, so that is exactly what is happening here. So for a star, all the activities happening in a star is in the core, not in the other surface. It is the core that matters. Okay, so star type based on mass. In star type based on mass, there are about 4 levels. We have the very low mass stars. Okay, the mass range from 0.08 to 0.5 solar masses. We have low mass star, which is from 0.5 to 8 solar masses. Then we have high mass stars, which is from 8 to 20 solar masses, and very high mass stars from 20, anything above 20. Okay, the mass of the sun is a standard, for measuring masses in the universe. So the mass of the sun is called as 1 solar mass. Okay, and it is about 2 times 10 raised to the power 30 kilogram. So I'm going to explain each of these masses as we go. So for the very low mass stars, we call them red dwarfs. Okay, like they are very small. Like I say, I have explained it before, that very small. So they do not fuse a lot of hydrogen. The rate at which they fuse hydrogen is very, very low. So that is why they are red. Okay, so here is the diagram. So they fuse it in the core. They fuse the hydrogen in the core. But something unique happens here. Because of the low size of the star, the whole star is available for fuel. The hydrogen in the star is available for fuel. So the fusion occurs at the center. Okay, then heat is generated to sustain the weight of the star. Then some of the particles close by gets heated up. Okay, they get heated up, so they become hot. So they move up. Then the ones that are up already, that are less, the temperature is less, they will move down. Sometimes they can even move into the core to be used as fuel. So this is what happens. The whole surface, the whole star is available for fusion. So that is how it works. The star is convective, and this is going to happen until the whole hydrogen is used up and converted to helium and sometimes lithium. So, like I said, they fuse very slowly, low radiation, and they look red. That's why, not really why we call it the red dwarf, but that's it. So the lifespan of red dwarfs are about 1 trillion. Okay, 1 trillion years. So the time it will take it to fuse all the hydrogen in the star itself is 1 trillion. Meanwhile, the universe, from the literature, is about 13.8 billion years. So you can imagine can come to the conclusion that these stars are just getting started. So if you do the math, 1 trillion minus 13.8, you would realize that they're just getting started. Okay, so they never become red giants. They never become red giants. So when they're about to die, hydrogen is exhausted. You understand? So we now have a helium core. We call it helium white dwarfs. It's a kind of core that is predominantly made up of helium because it is not massive enough to fuse the helium, so the helium remains there. So these helium white dwarfs eventually cool down to black dwarfs. Exactly, that is the fate of everything in the universe that is not a black hole. Now, we haven't discovered any helium white dwarf before because, like I've said, that these stuff are just getting started. So for us to have helium white dwarfs, we have to wait for the next 1 trillion years when they will begin to die. Now, these stars, these red dwarfs are the most common in our Milky Way galaxy. The most common, they're about 100 to 400 billion stars in our Milky Way galaxy. But these red dwarfs make up to 70 to 80% of all the stars. Now, these stars are also in the population 1 category and the population 2 category. I explained star population. Population has to do with the metallicity. It has to do with the stages. They understand. So the first ones are population 3, the second ones population 2, and the last ones in our epoch is population 3. So depending on where you find them in our Milky Way galaxy, for instance, if you find them in the globular clusters, they should be in the population 2. But if you find them in the spiral arms of our galaxy, they should be in the population 1. So that's where they are found. So they are in both categories. So here is the size comparison of a red dwarf with our sun. That's just a typical size comparison, just typical. So we have low mass stars. We call them the yellow dwarfs. Remember, not exactly that they are looking yellow. Some of them are looking white. Some of them are looking a little bit yellow. Okay, so we call them yellow dwarfs. So example of this star is our sun. Our sun is a yellow dwarf. It's just a matter of classification, not a matter of color, please. Okay, so just like the red dwarfs, they also slowly fuse hydrogen in the core. Now, because our sun is a yellow dwarf, it's a low mass star, I'm going to use our sun to explain about the mechanism of the yellow dwarfs, how they evolve and how they die. So taking that into account, I want you to know that unlike the red dwarfs, which the whole hydrogen, the whole surface is available for fuel, for a star, the whole surface is not available for fuel. In fact, we have the core. Even this one, even the red dwarf, we have the core. We have the core, which have half of the mass of our sun, and we have the other ones. Okay, so here is the sun diagram of the sun. We have the core. Half of the mass of the star is in the core, and that is where all the activities happen. Then we have the radiation zone, and we have the convective zone. Remember what I said about convection? Okay, in the red dwarfs, the whole star is available for fuel, but here the convection only happens at a particular layer. It doesn't even reach to the core, so take note of that. There are other layers, okay? We have the photosphere, the chromosphere, and the corona, but these three are the most important to us. So let us explain how it works. Now, what I'm about to explain, we apply to all the stars, okay? There are a little bit of changes, okay? But the process is almost the same, just a little bit of changes. But I'm about to explain can be extrapolated to other stars, I mean, even massive stars. So like I said before, in the core of our sun, there is hydrogen fusion. Hydrogen is fusing to helium and generating energy to support the structure, okay? And then the helium produced stay in the core. In fact, they start forming their own core in the core, okay? They start forming another layer around the hydrogen core, do you understand? So from the equation of pressure, pressure depends on height. and also depends on pressure. Sorry, on density of the material. So for instance, if you take water as an example, it is known that as you go deeper into water, the pressure increases. Okay, so if you take the density of water constant, gravity constant, height, if you keep descending downward, the pressure increases. So that is why down in the bottom of oceans, the pressure is very insane. No submarine can get there. Even some life forms can't even get there. But then when you have the density is now increasing for a star, because this same thing applies for a star. This density is now increasing. So the pressure is going to increase. So I want you to understand the picture. Then we have the normal pressure, okay? Then we have an extra pressure added due to the density of the helium, because helium is more dense than hydrogen. So the density is going to increase, and that is going to increase the output energy of the sun. So that is why, for the past 4.6 billion years ago, when the sun was formed till now, the brightness of the sun has increased by 40% because of this. So this mechanism of helium core, it contracts, and it contracts, okay, and adds more energy to the system. It often adds more energy to stars than the fusion. So they have two sources of heat. We have heat from the fusion, then we have heat due to the contraction of the core. So I want you to know that it is very important, because this is even more pronounced in the high mass stars. So now, when the hydrogen in the core is used up, they're all converted to helium. Okay, the deposit, the helium deposit becomes bigger, so the core contracts, pressure increases. Okay, now I talked about the radiation zone. You understand? This radiation zone is, the temperature here is not up to 10 million Kelvin. It can't fuse hydrogen. Remember, I told you all the activities in a star is in the core, not outside. So the temperature here is not even enough to fuse hydrogen here. But as the hydrogen in the core, he is exhausted, okay, and becomes helium. The helium contracts to generate heat. Okay, the heat increases even to the point of 10 million Kelvin to be able to fuse this hydrogen in the radiation zone. So, and that is when the star will begin to inflate. However, I want to explain something. When this hydrogen in the core is exhausted, and when this hydrogen in the outer core starts to fuse, we say that the sun, that the star or the sun has moved, or is moving away from the main sequence. The real meaning of a main sequence is the star is fusing hydrogen in the core. So when that hydrogen in the core is exhausted, and maybe they start fusing hydrogen in the outer core, it is now moving away from the main sequence stage. So I want you to note that. And all this process is going to apply for all of this. So the star is going to be fusing the hydrogen in the outer core, converting it to helium and producing heat. The heat becomes more. Okay, the core will contract. The helium core will contract more because it adds more heat. So the star will begin to inflate. Hello? Hello, Danny. My view disappeared, sorry. Hello, Danny, are you there? Can you hear me? I want to know if you can hear me, because I think maybe my network is disturbing, or my video.
Yes, yes.
My video has disappeared. I don't know what happened. Let me, my view.
Don't worry, don't worry. What happened? Maybe Maybe your connection is not good.
Okay, I'm back. Sometimes my webcam gives me some little trouble, so
Okay.
it's back. I can see myself. So
Okay. Okay. Let's go.
all right, great. So I was explaining about helium fusion. My video has disappeared again. Uh, just a moment. Just a moment.
Yeah.
Let me change the port. The port where I slotted it.
Maybe switch off your cam.
Okay, back again. I've changed the port where I slotted it, so it's better now.
Okay.
So I was explaining the process at which a star becomes a giant begins to glow inside because of this additional heat due to the contraction of the core. So it's a gradual process. The sun is going to become a subgiant. From a subgiant, it becomes a red giant. Okay, when it becomes a red giant, it's going to become 150 times bigger than what it is today. Okay, then it's going to become 2,000 times more luminous because of this contraction going on there. That contraction adds more heat to adds more heat to the system. So when the sun becomes a red giant, remember the mass is the same, but it is just getting bigger. It is getting bigger and bigger. So when that happens, the particles, the matter at the outer surface of the sun would not be able to be held. Okay, the radiation pressure is increasing. Remember, the pressure luminosity is increasing, but the surface gravity is decreasing. The sun is becoming less dense. So this radiation pressure is going to push away this outer matter. When it pushes it away, we call this planetary nebulae. That's the first stage. This is the first stage. So in the first stage, when the sun becomes a red dwarf, it is going to eject 33% of its current mass. That's huge. So it is now having about 67 left. So that means it's going to move from its red giant stage to a smaller size. I mean, the size, is not getting too small, no. I mean, compared to the red giant, it becomes smaller, okay? And at the same time, as this hydrogen burning shell, okay, is happening, it is depositing some ash of helium on the core. So the core is getting bigger, more massive, and contracting. So the temperature is increasing. So the temperature will increase up to 100 million Kelvin, which is the temperature for helium fusion. So the helium in the core will begin to fuse. And be producing carbon in the core. So the carbon will develop its own core, its own layer in the core, just like when hydrogen was burning, helium was developing its own core. So when helium is burning, carbon is going to be forming its own core. You understand? Carbon is denser than helium and hydrogen. So from this formula again, the pressure will increase even more. Heat is going to be generated even more, and the output energy will be even more. So the star will become another red giant. So for the second stage, sorry, I need to work on my camera. The driver, I don't know. Sorry, I need to work on my camera. This is strange. So when helium is happening again, sorry for the inconveniences. Okay.
Marcel.
Yep.
Switch off your camera.
It's back again now. It's back again. I fixed it. So the same process that
Okay.
happened with hydrogen to helium is going to repeat itself. The process will repeat itself with um, helium to carbon because helium fuses to carbon. So when uh, helium fuses, okay, and becomes carbon, the same process is going to happen, and the sun is going to become another red giant. So there are two stages of red giants here. So during that time, it's going to shed half of its mass. Remember, it has shed 1/3 of its mass. So it's going to share half of what is remaining, which is half of 67% of what is remaining. So it becomes even less massive, even less massive. So the stage will come when there will be helium burning shell. So that will also inflate the star. The sun will lose so much mass that it won't be able to fuse carbon because you need a higher temperature to fuse carbon. Because helium burning is helium fusion is about 100 million Kelvin. So but carbon fusion is even way higher than that. So after that, because it could not fuse her carbon, no mass to fuse carbon, it is going to settle as a carbon white dwarf. So it becomes a carbon white dwarf. So here is the size. Here is the sun. So here's the sun. When at this stage, okay, it is still a main sequence star at this stage. So here's the diagram, the magnified diagram. And here is going to be the sun when it becomes a red giant. Okay, so you can compare the size. But here it's going to become, in the red giant, it's going to be less dense, okay? Very much less dense than the sun. So it's going to lose its outer layer as planetary nebulae, those beautiful colors you see in astrophotography. So here's the summary of the process, although it's not, or just a little bit of summary. So from the collapse of the giant molecular cloud to main sequence to subgiant and to supergiant and to white dwarf. So that is the process. Now, white dwarf is supported by what we call electron degeneracy pressure. An electron is a fermions. Okay, fermions are some group of particles, okay? Group of particles that obey the polar exclusion principle. It states that no two fermions can occupy the same quantum level simultaneously. It's a quantum problem, okay? So, but these fermions, everything is made up of fermions. Everything is made up of fermions. This wall, fermions, you and I, okay? Fermions are used to build structures, okay? Some bosons can build structures. So this white dwarf, because it is no longer fusing anything to produce energy to sustain the mass, it is this electron degeneracy pressure that is sustaining it. So it can't collapse further. It remains in that state. So later on, white dwarfs will cool billions of years, will cool to black dwarfs. And that is actually the end of everything that is not a black hole. So here's the diagram of planetary nebulae. Okay, so this is the helix nebulae. This is the ring nebula. We process this in our lab. So we capture this using the Las Cambres Observatory. And we capture this using okay, we got this data from the James Webb Space Telescope. So we call this the planetary nebulae. Okay, so our fate, what is going to be our fate when our sun begins to expand? All right, so at this moment, okay, from the last 4.6 billion years till now, the sun has been fusing hydrogen in its core. So it is still fusing iron in its core. Then it still has about, from now to the next 6.4 billion years to fuse this hydrogen. Okay, for the hydrogen to be exhausted. So you still fuse, continue fusing in the future, up to 6.4 billion years. And if you add them up, it becomes 11 billion years. So after that stage, after 11 billion years, okay, when the hydrogen in the core exhausts, the core will contract, it will exude heat, okay, then the temperature outside the core will increase to start fusing hydrogen in the outer core. So that is when the sun will begin to expand, okay, and this is when it becomes very dangerous. So at that point, it is no longer safe to remain on Earth. So we have to find a place to go. So as the sun begins to expand, it is going to expand even past the orbit of the sun, of our Earth. It's going to expand past it. You understand? So what is our fate if we begin to expand? Will the Earth remain there? Will all the planets, all the planetary system remain in that position? And the answer is no, they would not remain in their position. Because remember what I told you? I told you when the sun begins to expand, the gravity, it is going to be losing mass, okay? Because the surface gravity is going to reduce and the pressure, the radiation pressure is getting higher and higher. So it is going to push out those materials at the surface. So it's going to lose a lot of mass. So that is just for the sun. Even for the planetary system, it will not be able to hold them in place. So they're going to move outwards to counterbalance the changes that is happening. Okay, so they're going to move outward, and then, in fact, all these other outer planets like the Jupiters, the Saturns, the Neptunes might even be flung into space because the gravity may not be able to hold the system together again. And that could be the origin of rogue planets, okay? That's what I'm suspecting rogue planets are coming from. So from these dying stars. So, but before that time, we should prioritize making lives multiplanetary. Okay, this is one of the reasons why we are, working so hard to discover exoplanet. We are making a lot of research on exoplanet, okay, so that we can find another habitable world to live when this happens. This is a very big catastrophe. So we want everybody to join, and we have a program on that in our research lab. So that is the end for the low mass stars. Then we have the high mass stars and the very high mass stars. I want to combine them together. The high mass stars. So high mass stars, remember, they start from 8 to 20, then 20 and above. So the high mass stars, they do not stop at carbon because they are more massive. They do not stop at carbon because they are more massive than low mass stars. So they're going to fuse carbon because of the contraction. Heat is going to scale up. So look at the temperatures here. The temperature required to fuse, the minimum temperature required to fuse hydrogen, helium is 100 million Kelvin. I've mentioned that before. Okay. So when helium is fusing to produce carbon, there's going to be contraction. The heat is going to increase. Once the heat is up to 600 million Kelvin, carbon will begin to fuse to form sodium. So but look at this, I put this element in the bracket because they are also produced in traces. Like when helium fuses to carbon, it produces some traces of oxygen, nitrogen. So when carbon fuses, it gives rise to neon, and then we have traces of magnesium and sodium. You understand? So that's why I put those ones in brackets. But the major thing is the neon and the carbon. Then when the temperature, so that for sodium, the temperature to fuse sodium is 1 billion Kelvin. So the temperature of fused neon is 1.2 billion Kelvin. For magnesium, 1.8 billion Kelvin. For oxygen, 1.5. And for silicon, 2.7 billion. So you see, it is getting brighter and brighter. So that is what is happening here. But I want you to know something here. The period it will require to fuse each of these layers is getting lesser and lesser as the elements are increasing. Okay, so here is what I mean. I told you in the last class, I told you for a very massive stars, those massive stars, they live within, their lifespan is in millions of years, hundreds of millions of years, okay? So for instance, the hydrogen we could just fuse within 100 million years, okay? So when that is exhausted, we then have helium. It will take helium 1 million years to fuse. Then it will take carbon 1,000 years to fuse. And if we take neon 1 year to fuse, then it will take oxygen few months to fuse. And silicon one day to fuse. So here is the layer. So here you have to have the hydrogen, helium, then you go down, okay, until you have the iron core. So when silicon is fusing to become iron, something dangerous begins to happen. Let me move this let me move this down. It's blocking me. Excuse me, let me move it down. Okay. So I said in the last slide, when iron begins to be synthesized in the core, iron does two things very terrible. Iron does not produce heat. Iron absorbs heat. And not only does it absorb heat, it also absorbs the electrons that are wiggling around. Remember, I told you the heat supports the star, the structure of the star, and this electron also supports the star too. You can see that in white dwarf, like I explained in the electron degeneracy pressure. So, but when silicon is fusing to become iron, this iron will begin to be taking away this support system. So imagine
Oh, yes, Marcel is coming back. Let's wait. He's fixing his trouble. So if you, yes, you can do everything now.
all right, so when silicon begins to fuse to synthesize iron, like I said before, iron will begin to absorb the available heat and the electrons around. So, okay, I've mentioned this before. The lifespan of all these high mass stars is between 100 million years. Okay, it's in the hundreds of millions of years. It can be 200 million years, 300 million years. They are very luminous, okay? So we have high mass stars and very high mass stars. So this is high mass stars and very high mass stars. So now the high mass stars are going to become red supergiants, while the very high mass stars are going to become red hypergiants, okay? So these are some of the information that I missed. Then we have, so the ion core will absorb the heat and the electrons. And then once these support systems are out, then the core is going to collapse and a supernovae is going to result. So we call this type 2 supernovae. So here is it. So that's supernova is a core collapse when the support system is out. So now, what results when the core collapses? Okay, because when the core collapses, something is left at the middle. Okay, so whatever remains will depend on the initial mass of the star. So for those stars that started out their lives with masses less than 20 solar masses, they are going to, when they collapse, you know, and explode in supernovae, they're going to form what we call neutron stars. Okay, for those ones that have masses greater than 20 solar masses, they're going to form black holes. So now, supernovae are very energetic event, okay? When supernova explodes, it is it can outshine all the stars in that galaxy. And in fact, we can see supernovae halfway in the universe. You know, the diameter of the universe is about 90 to 92 billion light years, okay? So half of that is about 45 to 46. So we can see supernova explosion 45 to 46 billion light years away. So that should tell you how energetic. And because they are very energetic, the process, because you know we have these layers, they are still there. Okay, so some of these layers could, the pressure, the energy could, you know, fuse the nuclei to form heavier elements like gold, uranium, silver, nickel, fluoride, and calcium, all of these heavier elements. So supernova explosion can even create new elements. So like I said before, it can trigger a star formation. I have used this slide, I have used this simulation before. It can trigger star formation. So that's the process. Now, for a given galaxy in 100 years, that is expected to have about 2 to 3 supernovas in 100 years. Now, to be in the danger of a supernova explosion, you need to be at least less than 100 light years, okay? But for us, we are not in that danger line because the closest star that could experience a supernova is about, that's the name IK Pegabis B, is about 150 light years away from us. So we are far, far beyond the danger zone. And that star is going to explode as a type 1A supernova. That star is a binary system. So the kind of supernova is called type 1A supernova. I will explain all of these things in the future because we still have a lot of things to cover about stars. So here is the summary of the evolution of high mass stars. They start out their lives as massive stars. They become red giants. They explode depending on their initial mass. They can either become neutron stars or black holes. And so here is a remnant of a supernova. So for the low mass stars, we call them planetary nebulae. For the high mass stars, we call those other gases and dust that spews out as supernova remnants. So take that, and that's a Crab Nebula there. So here is the diagram of them side by side. So this is a planetary nebulae helix, and here is a supernova remnant Crab Nebulae. So I want to see the difference between the two of them. So for the planetary nebulae, they form from low mass stars, but for the supernova remnant, they form from high mass stars. Then another difference is that remnants of the planetary nebulae, they often form symmetrical round shapes with colorful glowing shells. Look at them; they are symmetrical, okay, organized in a way, and they can only find hydrogen and oxygen and helium. Okay, this red line is hydrogen. Okay, it's hydrogen, okay? But for this one, they are chaotic. For the supernova remnants, their structure is usually chaotic. You know, it's an explosion. So they are more chaotic in appearance than the planetary nebulae. Another difference is that for planetary nebulae, they last tens of thousands of years before they disappear into space. But for supernovae, they also last tens of thousands of years to millions before they disappear. So they stay longer than planetary nebulae. So here's the summary of all the things I've talked about stars. So it starts out as small, medium stars, you know, collapse of the giant molecular cloud. Here is high mass stars. For the low mass stars, here is their size in the main sequence. So they evolve to red giants. From there, they evolve to planetary nebulae, and they die and become white dwarfs. So for the high mass stars, they become very large. They become red supergiants or red hypergiants. Okay, no supergiant, hypergiant. Then we have the supernovae, the exploding supernovae, and they form either neutron stars or black holes. How about brown dwarfs? Brown dwarfs are failed stars. Remember what I said about stars? For a star to become a star, it has to be fusing hydrogen in the core. Now, before a star can fuse a hydrogen in the core, it has to have a minimum mass of 0.08 solar masses. Okay, brown dwarfs are not up to that. Okay, they're not up to that at all. So they're not able to form a star. We can't call them star because they're not able to meet that criteria. Okay, so they are failed stars. So we regard them as failed stars. So the minimum mass of stars is, I said, okay, 0.08 solar masses to 80 or 80 Jupiters. Okay, that's 0.08 to 80 Jupiters. So, but one thing about these brown dwarfs, that are intermediate between gas giants. Example of gas giant is Jupiter. Okay, we have Saturn, but let's use Jupiter. Okay, so they lie between Jupiter and low mass stars. So Jupiter is one Jupiter, then 80 Jupiter is the size of the minimum mass of a star. So their masses range from 1 to 80 Jupiters. So brown dwarfs can have masses of 60 Jupiters, 75 Jupiters, 30 Jupiters, but they are not able to fuse hydrogen to helium because they are very less massive to do that. So they are failed stars. They are failed stars. Jupiter is not a star, so it is not even a failed star. So some people regard Jupiter as a failed star, but that's not true. Now, what does this brown dwarf do? They emit in infrared, okay? They emit in infrared, not even invisible in infrared. So they are very hard to spot. They are very, very hard to spot. So even their first discovery was in 1995. So you can imagine just recently, I have been born before 1995. So I was born in 1990. Okay, so they are called brown dwarf does not mean they are brown, okay? Don't always use this classification to mimic, to think they are the colors. They are not really the colors. They're not really the colors, okay? So they can be, the colors can range from magenta, dark orange, red. The brown there has nothing to do with the colors. So I want you to know that. So in the Milky Way, we know in the Milky Way, we have about 100 to 400 billion stars, okay? But for these brown dwarfs, they are very much a number. They are about 25 to 100 billion. So they are very much a number, very much, because they are very small, so it's easy to make them. So the nearest brown dwarf to Earth is about is in distance of 6 to 6.5 light years away, very close. And there could be other brown dwarfs close by because they are very hard to spot. So let me talk about star types based on spectra. Star types based on spectra. Back in the days when astronomers were making enormous discovery in astronomy, they wanted to know the temperature of all these stars because it is very hard for you to measure the temperature, without any knowledge as we have today. So you can't go up there and stick and put like you put a thermometer and to measure temperature. You can't do that because you can't go to the stars. So how do we determine the temperature of stars? So they have to come up with another smart way to measure the temperature of stars. We have what we call an incandescence. Incandescence is a material. If you heat it, or even an iron material, if you put it on fire, and as the temperature increases, the color also increases. So it moves from red to orange to white to blue. You understand? So the temperature is indicated through the color change. So the red corresponds to lower temperature, and that is longer wavelength, and the blue corresponds to higher temperature, shorter wavelength. Okay, so this Wind's displacement law is used to describe this relationship between temperature and the wavelength of these stars. So here the simulation. So stars that are less massive, the temperature is low, looking red, while those ones that are temperature are very, very high are blue. They get, so the bluer, the higher the blue, the more the temperature. So that's exactly what is happening here. So based on spectral types. So with that in mind, so everything was classified. So the red ones We call them M stars, followed by K stars, G stars, F stars, A stars, um, B stars, O stars. So the color increases, the color of white light, those spectrums increases across. So you can use this acronym, O, be a fine girl, kiss me. So that's what we use to describe it. So as astronomers were able to deduce that that these colors of stars are also intertwined to their size. Okay, the massive ones are blue, while less massive ones are red. So I explained that before, why they are red, because the fusion rate is less. Why? To sustain their lifestyle, the fusion rate is less compared to those massive ones. They fuse a lot of hydrogen. They fuse a lot of stuff in their core to be able to generate enough heat to sustain their lifestyle. So you can imagine that. So those massive ones are blue in color. So if you look up in the night sky and you see the stars, they have colors. The stars have colors. Although your eyes may not be able to distinguish that, but stars do really have colors. So that is the color correlates with size and luminosity. So the whole thing was summarized in what we call the Hertzsprung-Russell diagram. Hertzsprung diagram. So here, the horizontal axis is the temperature. The vertical axis is the luminosity. Okay, so temperature increases from right to left, while the vertical axis is logarithmic. This is logarithmic, okay? So if you arrange all the stars in the Milky Way galaxy, just none of them, the ones we could find, they will all lie here. So these are the main sequence stars, okay? These are the main sequence stars. All stars started out as main sequence, but as time goes on, okay, when I explain what happened in the core, they begin to move away from the main sequence stage to giant stage, and from there, they end up being white dwarfs or black holes. So if you also observe that they are color coded, they are color, so those those ones that have lower temperatures, those red dwarfs, look at them here, and those ones that have higher temperatures, those those giants have higher luminosities, so blue colors. So my lecture has ended, but I want to demonstrate everything that I have explained about this with the software. With the software, I'm going to, so this software gives you a simulation of the end of life of all these stars I've explained. So this software is online. I will send you the link after this lecture. I'll put in the comment section or in the description. So it was built by astronomers at the Las Cumbres Observatory. So you can use it to educate students about these whole processes I have just described. So I want to change here. I want to make it fast, not too fast. Okay. So here is the sun, here is the star. So I can change the size. I can change the mass. Okay. Remember we started, okay, the lowest we can have here is 0.2. That is within the low mass star, remember? Low mass star. So let us see the life cycle of a low mass star, like those stars that are less than 0.6 is less than the mass of the sun. So let's see how it goes. So I'm going to start this. If I start it, so observe what is going on for the low mass stars. Those stars, so they become giants, start becoming giants. Okay, then they die, they exhaust their fuels, so they become this. So these are low mass stars. So let me try it with our sun. Let me just that is mass of our sun is 1 solar mass. So let me try it so that you can see the life cycle of our sun, so that you can see all the things I've described. There's going to be 2 red giants. So the first stage is the hydrogen burning stage and the helium burning stage. So you can see that. So 2 red giant phase until it becomes white dwarf. So at this stage, this is where it shades off its mass and becomes the white dwarf. So let me do it for very massive ones, like 20. Let me do it for 20 solar mass. So let us see it. That is for high mass stars. Look at this cycle. So it's a little bit complicated, but almost the same physics. So boom, look at that. You can't even see what's happening there. So let me make it for 30. Very, very massive. So, and they evolve so quickly. Observe what is going on here. That's the millions of years. So look at it. Oh, the exploding supernovae. So here is the region of high mass stars, here's the region of low mass stars. And that will bring me to the end of my lecture. So I'm going to put this link. So in my next lecture, I'm going to talk about dead stars. I'm going to talk about all these dead stars like the white dwarfs, the neutron stars, and the black holes. So my lecture has ended. Thank you so much for paying attention. You can ask me questions in the comment sections and I'm going to reply you. Thank you. So Danny, Don.
Thank you, Marcel. Thank
Yeah.
you very much. It was a very good lecture. If you have any questions, just
Yeah, I'm expecting people to ask me questions. So
okay. Okay. Oh, wait a minute. Wait. Wait.